Okay, so now we're going to just prove a relatively straightforward theorem about limits of the composition of two functions. And so I have to say, actually, the book, so the theorem the book proves about this is actually slightly weaker than it could be. So I'll give you the stronger formulation of the theorem at the end. It's kind of strange because they say, like we might expect to be able to prove a more general theorem than this. And actually they could. I'm not really sure if this is like a mistake in the book or something. I actually just kind of discovered this as I was preparing this video, but there is like a more general formulation, which is also like almost trivial to prove, I think. Well, I don't know. We'll see. I'll show you the statement at the end. But so I think the good thing about the statement the book makes is that it gives them, it gives us reason to examine the following strange situation. Okay, so let me just show you a weird example of what can happen if when you're taking the composition of two functions if the outside function isn't continuous. Okay, so the issue is right. So well, okay, I'm gonna draw some graphs real quick. Okay, so here's an example where basically the limits of f and g are both perfectly well defined as x approaches, these two-sided limits at least are perfectly well defined. But the real issue is that f actually achieves the value 0, which is its limit as x approaches a, the limit of f is 0, and it achieves that value over and over and over again here. So the fact that g of 0 is just this random number means that f composed g is able to achieve this like weird exceptional value infinitely many times as you let x get close to a. So the limit here actually fails to exist, even though both of these limits actually exist. Okay. Now, again, like I said, there's an easy statement that you can make that gets around this problem. I'm not 100% sure why the book doesn't make the statement, but it is good to be aware that this kind of situation can arise. And so the way the book gets around it is just by requiring g to be continuous at this point. Okay, so I'm going to make the statement that the book makes, and that's going to be the theorem that we'll use going forward. Okay, but then I'll show you the statement that I think makes sense here, which is more general after that. Okay, so all right, so here's theorem 20.5. So let f be a function such that L, the limit as x approaches a along S of f of x exists and is finite. If g is a function defined on f of x, such that x is in S union L, which, remember, this is just, we like to write this as f of s, okay? And of course, yeah, we don't know if f actually achieves the value L anywhere in S. That's just the limit, right? But we need g to be defined there for the purposes of this statement. So, and let's see. So that is continuous at L. Then the limit as x approaches a along S of, so yeah, continuity at L is critical here. That's what prevents this scenario from happening, okay? Then the limit of g compose f of x as x approaches a along S exists and equals G of L. So I think maybe the reason that the book decides to make the statement this way is just because this is the only way you can make the statement that actually lets you describe this limit as being G evaluated at the limit of F, okay? So this expression G of L here, that's not gonna show up in the statement that I make later. I think that might be why. So you'll see what I'm talking about, but yeah, I think that might be because this way it's actually like, it's nice to really visually see from the way things are written down that like limits, you can pass a limit inside of a function basically. Yeah, so this statement really makes that very explicit, even though the statement that I'm going to make later, it would be immediate from that one that this is true for continuous functions G. But okay, anyway, so the proof here is like extremely short. So clearly G compose F is defined on S by assumption. Let xn be a sequence in S with xn having limit a, then we have L is the limit of f of xn. So by continuity of G at L, the limit of G of f of xn is the limit of G of f of xn is just G of L. I mean, that's by continuity, right? So that's it. I mean, that's the proof, right? This is G compose f of xn. So that's exactly what we wanted to show. Okay, so let me just make the statement that I think is like sort of more general in a way. Although, like I said, it doesn't make it as explicit that you can like pass a limit from outside a function to like inside the function. But yeah, you'll see. So we could also prove, and maybe this would be a good exercise for you to think about. I mean, it's, the proof is like kind of trivial, honestly, but it might be worth it just to think about it. So we could also prove the following, unless I'm mistaken. So if I'm mistaken in writing this, I'm sorry, but I'm pretty sure this is true. Let f be defined on S with the limit as x approaches a along S of f of x equals L1. Let G be defined on f of S with the limit as x approaches L1 along f of S of G of x equals L2. Okay, and now you might be wondering, okay, how do we even know that this makes sense, right? Like, how do we know that there's a sequence in this set, f of S, which approaches L1, right? Well, the reason we know that is because any sequence approaching A here gives us a sequence, any sequence of points in S approaching A, by evaluating F on that sequence, we get a sequence of points in F of S approaching L1, right? So this is, it's automatic that that there's at least one sequence like that, because there's at least one sequence in S approaching A, okay? So so this symbol, makes sense on those grounds, and then we're supposing that it exists, that it has a value in equals L2, right? Then what we can say is the limit as x approaches A along S of G compose F of x equals L2. That's the statement. And so you can see from here that neither L1 or L2 is expressed as like the value of one of these functions, right? L1 may not be f of a because f might not be continuous at a. Similarly, L2 might not be g of L1 because g might not be continuous at L1, but it doesn't end up mattering in the end. Like if you phrase things this way, then this just works. And then, so like L2 kind of plays the role of g of L1, right? Except it's just accounting for the possibility that g might not be continuous at L1. So that's why we just put L2 here, right? So I don't know. Yeah, I'm pretty sure this works. I'm like 98% sure this is true. Okay, I proved it in my head. I proved it in my head before starting the video. So I'm pretty sure this is true. I don't know. Yeah, maybe if one of you can come up with a counterexample, then please let me know. That would be great. But anyway, yeah. So in the next video, we'll start converting these we'll find like epsilon delta type properties that describe each of the limits that we've defined. So yeah, that's it for this video.